In this tutorial segment, we're going to discuss how to model post-tensioning in the slab. And we're going to model both banded and distributed PT. We're going to manually enter the PT, and we're going to use pre-compression requirements as the basis for the manual entry. And we'll assume CG values from the top of the slab, or the top fiber over support, and from the bottom fiber at midspan, and then the anchors being 1/2 the depth of the slab. So we're also going to consider the fact that we have beams, and we're going to assume that the beams are participating and are post-tensioned. So we may not want to max drapes out, but we're going to assume that to begin, and then in the course of the design we can always modify the drape of the beam if we have too much uplift or reversal of stress that might be harmful just to the design. So to start, we know that for this particular strip, for example, the required pre-compression is going to, or the required number of strands or total force will be a function of the area and the target pre-compression. So the area of the section might be 2620 inches squared. That's kind of the maximum area at one of the sections over at the far right. And this is a fairly prismatic strip, so the area at the far left, if we were to go to one of those section cuts, you can see this area is 1980. So it's pretty close. This is in a location where there is no beam. Obviously it's much smaller, but if we go to one of the section cuts at the beam, we get 2620 on the far right and 2550. So they're pretty close over the beam, which means that if we assume that we want to target a pre-compression of 150 for this zone, we need 15 strands. We're going to take 150 times 2620, and that equals 330 kips divided by an effective force of 27 kips per strand. That's essentially a 1/2 inch diameter, unbonded monostrand, effective force anywhere from, let's say, 26 to 27 kips, or 118 kilonewton equivalent for SI, and we'll target 15 strands on this particular line. So we'll go ahead and do that. We'll go to tendon. Under tendon heights, we want to dictate the default tendon heights from top fiber and bottom, and then we'll use 2 and 2.5 for the beams. And then we'll just go ahead and add a tendon. And we can add 2 tendons, we could add 1, we could add 15, we could represent half of them. But here we're just going to add 1 tendon line equal to 15 strands. And I usually like to add those off of the support line. That way it doesn't conflict when you're trying to select the support line. So I'll start at the left end, and I'll turn on the snap orthogonal, and then I'm just going to snap near supports. So you can see if I move away from that, you can see this green line, which is actually the spline. It's a representation of the spline, or the curvature of the tendon should I snap at this location, and it's there to give the user an idea or an approximation of where the tendon would end up if you snap at that point. We're going to keep the y coordinate of this tendon at the same point, meaning the tendon is essentially linear. There's no in-plane curvature, so you don't see any curvature for this particular tendon. Now if I move one of these points, now you see curvature because we're using, under tendon settings, we're using spline tendons. You can turn that off and have everything linearized, or you can actually represent curvature in plane for the tendons if you need to, using the spline option. So we'll go ahead and just undo. You'll notice I have a live and a dead end representation for the cable. If I double click, we're going to set this equal to 15 strands. They're 1/2 inch diameter strands. And if I go to system friction, you can see they're unbonded. Those can be changed also to bonded if you're using a bonded system. The stressing we're assuming is 27 kips per strand, or you can have the program calculate the short-term losses for you if you select calculated force method with a lump sum of long-term loss. We'll use effective force. And then for the shape of the cable, we have to we have to define the shape. So the only modification we'll make is we'll make this a straight shape at the far left end where the tendon exits out of the slab. So we'll go to straight, and this will become 4, and this is just straight in, and it starts into the drape. Again, we're maxing out the drape, and we can make refinements in the course of the design. So we'll know, whether or not we have too much balancing, or we have a reversal of stress, for example, based on so much drape in these beams. Okay, so there's tendon 1. I'll go over to this opposite side, and this is roughly equal to the other side. It's just flip-flopped. So we're going to model always left to right and bottom top for the tendons. So we want to make sure we have a good standard and a consistent approach to modeling the tendons. You want to be able to look at the tendon in the tendon viewer that we just saw, and be able to correlate that with what you're seeing graphically in the model. So here we have live dead again. We need to flip that, and I'll go here to stressing. This is going to become dead live, and now this shape here gets changed on the far right end. This becomes straight. Change that to 4, and we have a similar tendon on this side. Okay, we'll start now with this cable. Now, what we're going to do here is we're going to do an add tendon. So we're going to create a tendon that is all the way through, live. It's going to be based on the requirement of P/A for this throat area where it reduces down in section, and then we're going to add tendons here and add a tendon here, because this is roughly 2 times the area on the ends. So I'll just double click on one of these sections in this throat region, and you can see that the area is 2470. Okay, so and that actually includes a beam. Those beams aren't technically post-tensioned. So what I want to do, you can see this, if I double click on this section cut, this includes that beam stem, and this is 2480. So we know that the width is 262 inches, and the slab depth is 8 inches. So we'll take 262. We'll multiply that by 8. Okay, so the area is 2,096 inches squared. If I multiply that by 150, that's my pre-compression I'm targeting, and I divide that by 1,000, you get 315 kips. That's the requirement. So we'll go ahead and take 315 divide by 27 kips per tendon, and we need 12 strands in the throat. In the other region, outside of the throat, we have 423 wide section. So we'll take 423, and we'll multiply that by, again, the thickness, which is 8 inches, and multiply that by 150. We need 514 kips. So if we take 514 over 27, we need 19 strands. We'll round it to 20. Okay, so we need 12 here and an additional 8 on either end. That's where we'll start. So I'll model back to tendon. I'll add a tendon, and I'll model this just on the bottom of the support line, like so. And I'll use orthogonal again just to make sure it's nice and straight. And we're going to do a snap on our control points. Here I'm going to turn off orthogonal just so I can snap, for example, somewhere, let's say, down here. And then I'll turn orthogonal back on. And I'm actually just going to go all the way across. This will be a straight shape because we have so many walls there. And then I'll go back to non-orthogonal so that I can, again, maybe align this with these columns. Back to orthogonal. We'll end here. So we'll add a couple more points. And then I'll end by selecting perpendicular to the slab edge. Okay, so this becomes our tendon. Now, this is an idea where we have this curvature based on this spline setting that we're using. So again, if we wanted to bring this back in and we wanted to use splines, we could add swerve points. We have additional videos on the use of swerve points where we can right click, add a swerve point, and then we use those to control the in-plane curvature of a tendon. I'm just going to set this back to modeling these as linear, just for the sake of the example here. And if I double click, you'll notice this, we show a dead end here. We're going to go to stressing. We'll change this to live. We'll set this to 12 strands, we said. And then we need to change the profile. Now this profile here in the middle obviously is the most glaring in terms of requiring a change. We'll set that to straight. Now that is okay. On the ends we have, again, a straight shape. We'll set that to 4 and 4. And then the drape here, this is not a beam, this is a slab. So we might actually make a modification to the low point from 2.5 to 1. And also from the high point, we'll say 1 here. And I'll go back and just modify that back to 4. I'll modify this end to a straight shape. And we have 4 and 4 there. And we'll say OK. So that dictates that first tendon shape, and then again we need to generate tendons on the opposite side of this particular set of columns. So I'm actually just going to copy. I'll do Control-Shift-C. I like to use that command just to nicely copy these things, and then we'll use Snap to Nearest and just align that, let's say here. Okay, and if I double click on this, I can make changes. This is going to be 8 strands. We had 12 plus 8 equal 20. This becomes the shape of the cable. Again, I'll make changes here to 1 and 1, and then the end spans will be 4. We'll do the same thing here. We'll do Control-Shift-C. I'll turn off Snap to Nearest just so I can select that a little bit easier and turn it back on to insert it. Okay, now in this case I'm going to use a different tool to modify the CGs. If I turn on the tendon editor, this will automatically show and display the CG, and I can modify the CG based on these settings. So here I'm going to say the CG is 1, and I'll just click on the points that I want this to be 1 at, and it happens to be the low point, the high point, and I can also just window select. Okay, this really needs to be 4. That's our end span, so this is 4 and 4. And then on this end, this is going to be, I believe, 6. Okay, so we'll say this is 6. Oops, we'll apply that. Let's try to window select it. So what's going on here? Let me exit out of that. This needs to be 6. Okay, this slab is actually, it needs to be 4. That slab is only 8 inches. Okay, so we have 1, 1 all the way through to 4 on either end. Alright, so we have our tendons now on top beams, middle, this is more two-way slab. This is still a two-way slab, but we have kind of a band beam there. The beam's technically a beam, not necessarily as wide as what might traditionally be called a band beam, but we're using it similarly. And then we finally have the lower design strip. Again, this is purely prismatic all the way through, so I'll just randomly select one of the cuts, and the area is 3250. Okay, so if we take, we'll clear that, we'll say 3250 times 150 is 487.5 kips. Okay, so we'll clear that. We take 487.5 and we divide it by 27. We get 18 strands. Okay, so we're going to run a cable through here with 18 strands. We'll go back to tendon and add the tendon. And again, I'll use snap orthogonal just to align it. Turn off snap orthogonal so that I could snap perpendicular to the edge of the slab. This should be live. Okay, so this is, let me say 18 strands, 27 kips for the effective force. We're going to set this equal to straight on both ends. Okay, this is 4 and 4. We're using that 2.5 2 CG because it's a beam. And then for stressing, we'll say it's live and live. Technically, the stressing end is just a graphical representation because we're using effective force. It doesn't really mean anything to the calculation. It would if we were using calculated force. And we have our tendons like so in the X direction. Now, in the Y direction, we'll go ahead and go to floor design, and I'll change the direction of the strips. In this direction, even though we have distributed tendons, the location of these strips on either end and the fact that the strips are pretty uniform means that we're just going to, we can take the opportunity to just add bands. So we're going to do band, 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 and we know in reality this is going to be distributed out based on whatever the requirement is for strands here. We'll do the same thing here. And then for this zone, we're actually going to show distributed cables through here in the model. Okay, and we're going to take advantage of the use of tendon mapping for 1, 2, 3, 4, 5, and then we're going to add these manually on the ends. So we'll start by adding these tendons. We know that in the other direction, if I turn the tendons on, the tributary for this tendon here is roughly the same as this one, so I'll just basically copy it. We need 15 strands. I'll go from bottom up, and here again we're going to add these manually. So we'll start down at the bottom and using snap to nearest and also snap orthogonal. Do something like this, where we have a small cantilever on the top end. I want to turn off snap orthogonal so I can snap perpendicular to the edge. Okay, and we have, again, the bottom end will be the dead end, so I'll change that to 15 strands. Stressing will be dead live, and then the shape of the tendon will say here this is going to be straight. and then straight again on this side. Okay, we may not need this much drape in the second span, but again, that will be evident when we go to design it. And now I'm just going to take this Control-Shift-C, and I'll just copy based on this reference point, center of column, and I can use the snap endpoint to locate that, and I'll go ahead and just add that tendon here. Okay, and then double clicking on the tendon, we may want to just verify the shape here. It looks identical. Here we can actually copy without any negative side effects like mirroring or rotating would show like a reverse in what you're seeing in the tendon property window versus what you're seeing on screen. So that is not always conducive to being able to cleanly see and understand what you're modeling. Okay, so we use just the manual input again, that method for the two beams. Now we're going to use what's called tendon mapping for these tendons here. And we'll select all four. We're going to go to Map Banded Tendon. We're going to use the design strip width as the target tributary. And we'll put in our targets for minimum precompression and balance loading. We want to idealize the tendons with a 1 foot offset either side of the strip. The assumed effective force, again, will be 27 kips. The end span, the first and last spans, are going to be cantilevered down, and then the interior spans will be reverse parabola. And we have just the default inflection points that can be modified here, or we can leave them as they are. We'll leave them as is, select OK, and you'll notice that the program will generate tendons straddling either side of the support line for these strips. And if we double click on one of those cables, you can see we need 21 strands per line. Now, this seems a little bit high. If we take 21 times 2, that's 42 strands. And the reason that's happening is because one of the design cuts may be passing through a beam. And or the beam, let's say the beam depth multiplied by this width results in that particular requirement, which isn't technically correct. So what I'll do is double click on a strip. This is 360 by 8 inches. So if we take 360 times 8, I get 2,880 times 150. We need 432 kips. Okay, so we'll take 432 divided by 27 just to check. We really just need 16. So what I'll do, and that's consistent between 1, 2, 3, 4 support lines. I'll take this and we're going to select those cables, and I'm going to modify the selection. We'll go to tendon, number of strands, and we're just going to modify this to 8. Now I also could have just done this very easily, selecting tendon editor, and I can go to strand. Here I'll go to 8, and I'll say apply, and you can see the program will show the number of strands. I just select the cables here, and we're changing those all to 8. So I have to window select the ends like so in order for that to grab when you window select. Okay, so again, the reason that happened is because of the presence of the beams, and the beams being part of that calculation trying to dictate the number of strands. So we want to back check that if we have beams. So now we have 8 and 8 on each one of those strips. If I double click on the tendon again, we want to make sure that we have the proper geometry. So we have a cantilever down shape into this reverse parabolic shape. And again, you can see that we're not maxing out the drapes. The program has actually done some balancing for us. It's actually pushed this cable from 2.5 to 3.25. So if we assume that we're using 1, we're going to use 1 and 1.75, let's say. And what I'll do is I'm going to use the tendon editor again to manipulate this. So we're going to say the CG we're going to say is 1. I'll change these to 1. Come over here and I'll just change those to 1. over the supports, we have to be careful we don't select this one because that legitimately needs to be 2, so I'll kind of focus in there and change those to 1 and 1 here. If we wanted to increase the size of the font, we could do that using this setting under Visibility View Settings. For Tendon settings under Finite Element, I can change, for example, the symbol size to 5. Maybe I'll change the font size to 20. Okay, and that helps us see that value a little more cleanly. Going back to Tendon, I'll go to the Tendon editor again. You can see the font size has changed. So the other font size we're going to change is 1.75. This is easy to just Windows select, and again I'll change the supports to 1, and I have to be careful not to select the wrong button here or the wrong control point. Here we're going to change this to 1 and 1. Let's see, this one is also 1 and 1. Now I'm post modifying this because I didn't change the tendon height settings prior to banding or mapping the banded tendons. What are really distributed, but we're just representing them as banded. So that's why I'm having to post edit that. But you can see using some of these tools, it's quite easy to do that. Now we want to make the tendons for this distributed region. And here we're going to map distributed cables. So I want to generate what's called a master tendon. The master tendon will be from this location, and I'll use, again, snap to nearest to select a tendon here. It'll be perpendicular to this band, and it will be anchored somewhere here on this core. I'll flip the stressing end to live dead, and our assumption is we're going to use 2 cables per distributed line. Okay, and the program will space those accordingly based on the target balance loading and target precompression. So the number of strands is 2. The shape we're going to use is cantilever down, and for this we'll use a reverse parabola that goes up from 2.5. We'll change this to 1 and 1 here, something like that. Okay, so that's our master tendon. We define the master first, and then we use map distributed. And here we're going to use a similar target, 150 to 300. Because we only have one span, the program locks this unless we select reverse parabola. Then we can balance based on the reverse parabolic shape. We'll again say 50 to 90. We're going to enforce 8 times slab thickness in terms of the spacing, or we can use a maximum spacing of so many feet. If I select OK, the program will ask to select point 1 of 3. So it's mapping point 1, 2, and 3 over a range. The first point in that range we're going to say will be here. This is point 1, point 2, and point 3. And the program produces distributed cables over that range based on that input. And you can see there's quite a bit of difference between technically modeling every specific distributed cable versus just representing them as bands. And we could have represented these also as bands within this each of these tributaries. So let's go ahead and go to floor design. I'm going to turn off the strips and the tributaries, and we are now left with this tendon layout. If we go to visibility, render model, we'll rotate that, and it's always nice to be able to see the tendons in this view just to make sure they look as we had intended, and there's no strange shapes. Let's say on the anchors, that's usually where that happens, where we might have a kink in a tendon where we didn't modify the end, kind of a short end span or a short cantilever. I'm going to turn off the walls and the columns, and then I will scale this vertically by a factor of 3, and this allows us to see the tendon shape more closely. Okay, so this is what our tendon layout currently looks like. That will conclude this segment for this multi-segment tutorial. If you have any questions, please contact us at support@adaptsoft.com. Thank you.